Hello everyone. Welcome to our Frontier Topics in Vision and Language Spring 2021 seminar series. I'm honored to introduce Professor Wang. He's an assistant professor at the EC department at the University of California, San Diego. He received his PhD in robotics at Carnegie Mellon and did his postdoc at the University of California, Berkeley. His research focuses mostly on the intersection between computer vision and robotics. Is particularly interested in learning visual representation from videos in a self-supervised manner and use this representation to guide robots to learn. So with no more delay, let's welcome Professor Wang.
Okay, thank you for the invite and thanks for the introduction. So today I'm going to talk about some self-supervised learning techniques we have been recently developed to help generalize robot learning. So there has been a lot of developments in robot learning, like learning from vision input, like for example, grasping objects or poking objects. But all these approaches are still very far away to actually generalize to the real world applications, like cleaning up the kitchen in a mess. So we still don't see this kind of robot working help us to do this. So to going towards to this goal, to have a very generalizable robot to deal with complex environments. So there are a lot of approaches that is currently tackling this task. So one way to learn to generalize robot learning, I would call it approach is called a more data approach. So this is some data set that's collected from Stanford that they try to do this kind of grasping or manipulation of objects among a cluster of objects or different backgrounds of the bins. And then there are another attempts, which is trying to remotely control the robot to do this task. So you can scale up these kinds of data collections from mechanical Turkers or from people all around the world. So you want to scale up data collections and the diversity of data as much as possible. And then there is also one word from CMU. So basically you try to put the robots that inside people's home and then collect data that is under different like floors and different basically lighting conditions. So all these approaches are trying to collect as much diverse data as possible. I call it as a more data approach. And then a second approach is basically trying to use domain randomization. So you try to train in the simulator, and then you try to transfer it to the real world. And because there is large gap between simulation and real, so usually do a lot of domain randomization. For example, you can have these very colorful images on the left, rendering different backgrounds or different textures. And then hopefully the learning in this environment can be able to transfer to the testing environment, which is also have diverse textures and unseen color. So both of these approaches is basically trying to do learning or train a policy that is invariant to the environment changes. And the disadvantage of this approach is that it takes a lot of time to collect data in the more data approach. And there's always out of distribution environments. So there's always cases during testing, the testing data is, or the environment is not covered by the training environment. So it is also very hard to transfer across the robots. So once you collect data with one robot, you can learn something on it. But if you bought a new robot or there are some, the robot is getting old and then basically the physics does not match anymore. And then it's very hard to actually transfer the already collected data to the new robot. So instead of like learning the policy that is invariant to everything, invariant to the environment changes, invariant to the physical changes, just train on large scale. I think in these talks, I'm looking into a different solution. That is, can we actually adapt the policy to the changes during the deployment? So during we see a new environment or an environment with new vision textures or with new physical environment. can we actually adapt and transfer the current policies that we learn from the old environment, instead of just training a policy that is invariant to everything. So to do so, we basically can get some inspiration from the computer vision community. So we already have the self-supervised learning technique, which in computer vision, which can help us to learn very good visual representations that can be applied or transferred to many different vision tasks. So in just a little bit introduction of the self-supervised learning. So in self-supervised learning, you basically try to design a new visual task that you can actually use this task without using any human labels. You can just train the neural network using this self-supervised task signal for free from the human labels. Because you can get the supervision signal from the data itself by designing this kind of task. So it is called self-supervised learning. There are a lot of recent development, especially in the contrasted learning approach. Basically, they show that you can train a very good and general representation that can actually transfer to many different tasks and adapt to many different downstream tasks. And it is working even better than the image lab pre-training, that we use a lot in the computer vision community. And besides this kind of feature that is transferable to many different tasks, we also have some approaches that is using self-supervised learning that can be specialized to input a certain type of task. For example, in here, there's a task we defined, which is trying to learn correspondence between the objects in different frames in the video. So we can actually learn to track the objects by designing some self-supervised task. In here, specifically, this is a paper on designing using a cycle consistency of time, basically saying the object checking backward and forward should be consistent, and then use that as a self-supervised signal to train the representation specialized for tracking and correspondence. So inspired by this kind of work in the computer vision community, we can think that in self-supervised learning, we can always get these labels all the time for free because we don't need human to label this data. So we can actually use this kind of signal to help adapt the policy even during testing, because we can get the label for free, and then we can even use this label during testing. And then in the new environment, we can use this kinds of self-supervised learning and try to adapt the policy to the new environment without using any rewards or human supervision. And then we have some examples that help us to find visual correspondence using self-supervised learning. Inspired from there, we can also use this kind of technique to find correspondence for transferring existing policies. So it's going beyond visual correspondence. Can we also find correspondence in physics and then use it to transfer, once we have correspondence, say, between different robots, can we use this correspondence to transfer the policy itself? So I will introduce these two lines of work. Specifically in this talk, I will break down to 3 parts. The first part is I will talk about how can we learn use self-supervised learning to help to learn sim-to-real transfer in some robotics manipulation tasks, even under some distortion of lighting in the real world. And then I will talk about how can we do this generalization across physics and morphology. And here I'm showing that we can learn the correspondence between the robot, and then we can transfer the policy trained on 2-leg cheetah and to the 3-leg cheetah environment without retraining the policy in the new environment. And then finally, I will also talk a little bit about some recent progress in learning this policy that can be generalized across different tasks. Okay, so in the first work, I would like to talk about is the self-supervised policy adaptation during deployment. So in this work, we are trying to tackle the visual-based reinforcement learning. So in this particular task, this is a carpool task. So the goal of this task is you move this car along the frictionless track, and the goal is to control the car so that the stick will not fall down. So we need to train a RL policy, which first takes a few frames as input, and then the policy will take will output the action, and then this action will be used to interact with the environment, and this will then give us new frames as input to output the next action. So this is how one episode of reinforcement learning work. But the RL policy usually trained on the environment on the left. It is very hard to generalize to the unseen environment. And you can see if we directly transfer the policy on the left, train on the left to the right environment, it would just directly fail without balancing the state. So a very popular approach to kind of try to handle this problem is by using domain randomization. So the assumption is that if we see enough diverse environments during training time, if we train on large scale data and we see a lot of invariant things, so we can learn an invariant policy and generalize to new environment that is also very diverse. So there are some problems of this kind of domain randomization approach. So the idea is to train an invariant policy so it can randomize enough to cover the test environment. But if the randomization is too easy, so it will not cover the test distribution because the test distribution can be very different and can be very unexpected. So if the randomization is too hard, then it becomes very difficult for the RL to train to memorize a very large space of different textures and different color of environment. So eventually, this kind of thing becomes engineering task to tune how much randomization I should apply during training this policy. So this is not very ideal. So our solution here is that instead of learning a policy that is invariant to environment changes, we want to adapt the train policy to these changes during deployment. Every time we see a new environment, we can perform some online adaptation to adapt the policy on the fly during test time. So instead of training an invariant thing, we can train a flexible policy even during test time. So how can we do this, adapt the policy during deployment or test time? So ideally, what reinforcement learning do is given the observation, we do some actions, we can get the reward, and then we update the policy. That's how we train the RL policy. But during test time, the reward is usually not available, and then we do not have the signal to train this policy. So in this task, we basically trying to introduce the self-supervised learning task to try to provide the signal to update this policy even during deployment and test time. So specifically, the following is our approach. So what we do here is that we have this kind of framework that we basically can perform joint training of the self-supervised task and the reinforcement learning task. So notice these two tasks, they share the feature representation together, which is pi e. And then for self-supervised task, we have this pi s to basically handle this self-supervised task. And then we have a pi a basically output the actions given the images as input. So the self-supervised task we define here is basically learning an inverse dynamics model. So specifically, the inverse dynamics model will take two states as input, and then it will output the action in between. So every time we given a state and an action, we can generate the next state. So this gives us a triplet of data to train this kind of inverse dynamics model. So more specifically, if we have a state or image in t-1, and then we take an action in also t-1, and the simulator will basically give us the output of image or state in time t. And then we can give this two states as input to basically train our inverse dynamics model to estimate the action that is between. So because we already can get the actions from the past history of the episodes or buffer, So we can actually get this triplet data for free to train this pi-e and pi-s, the self-supervised model. And the objective is very simple here. So it's a control task. So we have actions on the torque, the position and velocity control on each joint of the agent. So what we do here is just L2 distance between the ground truth action and the predicted action to train this inverse dynamics model. And after this, and similarly, besides this, this self-supervised task, in the reinforcement learning task here, what we do is actually we take a few frames as input and output the future action. So you can see these two formulation is actually quite similar. For the inverse dynamics model, we input two states and output action in between. For the RL task, we input a sequence of state and output the future action as the output instead of actions before. So that is the difference between the two tasks. And then to predict the future action, we use pi-a, and to predict the action in between, we use the pi-s. And during training time, we kind of just perform joint training between these two tasks. So the main task, RL task, is basically we use J to represent error or loss, and then we use L to represent the self-supervised loss. We just sum them together, and then we train the parameters for pi-e, pi-s, and pi-a jointly. So that is how we train the model. The interesting part happening here is basically what happens in test time. So during test time, we do not have the reward anymore, and we cannot basically try to tune the legwork using the reward because it's in testing. But what we have here is basically we still have the self-supervised learning. We can still have obtained this self-supervised loss, this training inverse dynamics loss task, inverse dynamics model task to provide this self-supervised loss. So because of that, during testing time, we can still keep fine-tuning the legwork by using this self-supervised loss. Basically, given new frames as the agent is running over time in testing, we can still get signal to train the self-supervised task. And because the self-supervised task is sharing the feature backbone, which is pi-e, with the reinforcement learning task. So when the self-supervised task is helping the feature to adapt to the new environment, this feature at the same time can help improve the reinforcement learning task as well. So we basically use this way to use a lot of tasks to help improve the feature, which in return, which is shared with the reinforcement learning task. So it is helping the reinforcement learning task as well. During testing, we just keep giving every frame we obtain as the agent interact with the environment. We just keep updating the legwork and just keep running the agent and keep updating the legwork. So this is the approach. Are there any questions on this approach?
Yeah, go ahead. If you have one question, you can, yeah. So there is a question. So what if the testing dynamic is different from the training one? Or
Yeah.
how to, yeah, go ahead.
Yes, so that's a very good question. So in this work, we primarily handle the task that is only visually different from training and testing have large visual difference. That's the primary task we are handling. But in the end, we also show some cases where the dynamics or the physics from simulation and real, they're actually different. And then we can show that using this kind of inverse dynamics model task can actually still helps improving the policy when the physics is different. The reason is that the inverse dynamics model is actually capturing the actions during optimizing the self-supervised task. So the policies is at the same time, the action output is also adapting at the same time. So that's why it can also help. I will show examples later, help on transferring to environments that is different in physics.
And like a simple follow-up is like after adapting to the new environment, will the system still work well on the original environment?
Yeah, that's a good question. So the answer is probably not. So we did have tried that, still kind of work reasonably, but um, I think the key part here is that it doesn't matter because we actually it's different from domain adaptation or general continual learning. You care about catastrophic forgetting. In our case, we actually only cares about to continuously adapt to the current environment, as long it is actually the best if we can overfit to the current testing environment. We actually don't care about what happens previously. If there's new data come in, we just overfit to the new data. And then new environment keep coming in, we just overfitting to new environment. We don't care about what have seen before because we can just keep adapting.
Yeah. And so like the final question is, are the theta s and theta e parameters shared?
Theta E and theta S share the same weights? No. So the theta S is for the pi S legwork. The theta E is for the pi E legwork. So it's actually different set of weights. So specifically, theta S is just a few fully conducted layer, and then pi E is actually a convolutional neural legwork.
Okay.
Yeah, that's a good question. So then it becomes a lot. There's a lot work on this kinds of like intrinsic motivation kind of work that you use prediction tasks to give you some reward to learn the task. Yeah. So there are many other ways to design this reward function. Do you mean that if the model adapts to the within? So I was so there is actually some study we have done that it still can perform reasonably well on the old task, but it will perform slightly worse. But if we do the testing again on the original environment, we can also do the same adaptation on the original environment. So we can adapt again back to the original environment. So it does not matter whether it is forgetting because we can just keep adapting. Okay, I guess this is the
Yeah,
questions
that's it.
for now. Okay, let's see some results. So we have done two types of experiments. One is the DeepMind control suite, and then the other is the sim-to-real manipulation. So in DeepMind control, we just do some very simple, actually only visual changes, like we have different backgrounds, and then we also have even a dynamic background. Specifically, I will show later that we have a video behind this task. But in this case, specifically, we want to balance the SIG on top. And we can see that in this video, in the between, there are two baselines that do not use the adaptation during test time. And in our case, we can see that even though it does not work well initially, but it converged to a very good solution because the features start to adapt to this new environment. And then we also have cases like where the environment is not stationary. So you can see that these two baselines in between works reasonably well, but as there is a very large distortion in the background, it just fail. But our approach is basically keep adapting to the changes. So here is another example. So the task is a half cheetah. So you basically want the half cheetah to run as fast as possible and as far away as possible. You can see our half cheetah is keep running, and this is getting stuck in between. So besides this DeepMind control suite, we also do tasks in real robot. So it's very important to understand our work and then illustrate actually work in the real world. So what we do here is just a simple task. Is visual input. You pushing task with visual input. So you basically want to push this yellow box to the red goal, and then you only take the image as the input to train this policy. And if you do direct transfer in the test time, so we've actually bought the disco light to the lab, and then we basically use this light to add some distortion, and then you can immediately see that the arm will fail to transfer to this dynamic environment. But using our online adaptation, we can basically keep adapting to this new environment, even though there are some light changes. And then another case is basically we can also do transfer to when we put the table sheet on top, and then we can also do a better transfer there. And then notice that it's not only the visual changes, the vision input is changing. It's also the shape is actually give you a lot of friction. So we actually need to put some pounder inside under the cube. So in this way, we can see that even there are some physical changes, we can still adapt this policy on the fly in the new testing environment. Yes, the model will be adapted to the most recent environment. Okay, so that's the work in here. So are there any more questions? Is this a real world on the right? Yeah, so on the right side is two real robots we're experimenting. So I guess because simulation nowadays too good, you cannot distinguish. During, yes, the whole point is you keep learning the model during testing. You just but it's not using the reinforcement signal to learn to learn the policy, but using the self-supervised learning signal to keep learning the model during testing.
So it does the robot get a top level view, or does it see this?
Yes, the robot is exactly seeing what we are seeing, just taking
Okay.
this image as the input. So change the environment. So then I'm not sure what that means. Change the environment more than once, but we did try like this same policy that train on left. We adapt to this environment, and then we also can adapt to this right environment. So
I
uh,
think he means like, did you like do one-time transfer? Then, if you a new environment comes, would you start from the original trained model, or can you do continual learning between like two
yeah,
models?
so I think this thing is kind of simulating that, although it's not completely ideal, but our goal is just we want the background is continuous changing over time. But I agree that you can still see they are the same domain. But yeah, but we haven't. I guess we have not have a very good design on how do you change switch to a very different environment over time. But in the last one it is to minimize the predicted action. How do you know the real action is good or not? So it's not a so the action. So remember the state. It is a triplet um, you get from interacting with the environment. So it is actually not the so this triplet is actually the ground truth. It's not a predicted thing. You can think of it as not predicted because you are getting the states after you use the action to interact with the environment. So now the inverse dynamics model is using the two states to output the action. So the state is actually, the training data is generated from the environment. To If the robot is put to a new environment, it will fumble the generation to yes. So the robot, if it's moving to a new environment, so it will probably is I think this example is more clear that in here that you can see on the right. So initially it just getting stuck a little bit, and then it gets better and better over time. So changing disco lights, yeah, that might be a good experiment. We have not done that. I guess it's actually every testing evaluation you take human trial to put the robot back to put the cube and go back. So we have not extensively tried a lot of experiment. What if the test environment changes a lot? Yeah, so I think a lot of questions is on like if we change a lot of in the test environment. So we kind of did that in simulation. So you can see this video background. It changes from blue sky to some star crossing, a very white background. So we kind of show in here, it kind of works when the background is changing a lot. But because the physical limitation, we didn't do very extensively in the real robot to show that happens in the robot. The share weights, but only train on the self-supervised class. So the whole purpose of self-supervised learning is actually just to basically to make the share part adapted, because it's only the share part that is used for the reinforcement learning head. It's not the self-supervised head is used for the reinforcement learning head. So that's why we need to change the share part. That's what makes it helpful. So during testing, only the PIE is used. So during testing, we train the self-supervised task using PIS and PIE. We fine-tune the PIE, and then we run the policy with PIE and PIE to generate the action. So the PIE is fixed, only the PIE is changing. Okay, I think I need to move on a little bit.
Yeah, sure.
If you have more questions, you can email me. So another thing I want to introduce is we can not only use the self-supervised learning to adapt the policy, but we can also learn the correspondence to make the policy transferable between different domains. So let's first go into a little bit on the computer vision side, the correspondence problem in the computer vision. So a very classic correspondence problem is just you try to find the correspondence between the pixels into two time steps. So you find the dog head is corresponding to the dog head in the second frame. And then people do tracking or optical flow. They are all kinds of these correspondence problems. And then in CycleGAN, we also see that we can transfer the zebra image into horse image and then transfer back. And then in here, basically the model inherently actually learns some correspondence between the objects, because you need to transfer the texture without changing the structure in here. And then you still need to maintain the eye textures and the leg is still in a good shape. So we kind of can define the correspondence in here in a more general setting, that we actually want to find the translation or transformation between two types of data or two domains of data. That's what we've tried to define, try to find in here. So when we move the correspondence problem into the robotics, there can be multiple types of correspondence problem in here. For example, we can still do this kind of simulation and real image kind of correspondence, translate between them. Or we can translate between the input image, which is the real image, and then the output is basically the state estimation in the simulator. That's one observation space correspondence. And then we can also do action space correspondence for two different agents in two different physical environments. So the action taken in the environment on the left will lead to a different results if you take the same action in the environment on the right. So there should be some correspondence between the action as well. So across different physical environment. And then there are when there are different morphologies between these two agents. So let's say I want to find correspondence between this 3 limbs swimmer and this 4 limbs swimmer. So we need to kind of translate in the state space and also translate in the action space because the dimension, they are all different. So how can we find this kind of correspondence between these two types of environment? So in this work, we are basically trying to design a single model that kind of unifying and the approach to find correspondence between the agents in two different domains across the observation and across physics and across methodologies. So just to give you the motivation, initially this experiment, what we do here is we just we put a robot arm in the environment, and then we kind of try to, given uncalibrated camera taking this robot arm, we want to estimate the arm pose in simulator. So what we do essentially, we just record the video, and then we have a random start position, and then we take random action in the robot arm in the real world. And then we can basically train a model to estimate the pose in the simulator without using any ground truth pose or ground truth state. Know that in reality, when we are playing around with the robot, we do have access to the internal states of the robot. But in here, we're just assuming that we do not have access to there, but we can still train a model to estimate the internal states. So we hope this can be further extended to other more complex environment that we have interaction with objects where the estimation of state of objects is not completely correct. But as a first step here, we kind of do this task to just estimating the state of this robot arm. So here are some results we showed. So we showed that given only the camera image, the video on the left as input, we can do this state estimation, or we can do translation to simulator given the results in the middle. And then on the very right is we try to train a CycleGAN in the image level to translate between these two domains. And here is one more example that you can see we are trying to move the arm left and right, and then in our approach we are able to generate the same left and right in simulator, but the CycleGAN kind of fails doing that. And then I think this is one more examples of up and down. So note that the model only takes the image as input and then output the states in between in the image in the middle. So how can we do that? So before introducing our approach, I would like to first go into a little bit background of CycleGAN. So CycleGAN, I think a lot of people already know that it basically tries to do some unpaired translation between two domains. And then you take the image on the X domain, you go for the G translator, you can translate to the Y domain. And then the Y image go for the F function, you can translate back to the X domain. And then you will say that going for these two functions, the X and the original X and the predicted X, they should be consistent after this true translation. So this is how CycleGAN works. And then there is some discriminator in Y domain and X domain to kind of to model the domain of these two data. But in this case, in the case of in the robotics environment, if we are not translating the image texture, we are actually translating the image into state representation, which is a set of XYZ of the robot joint. So CycleGAN will not work here because a lot of time what CycleGAN did is they just maintain the structure of the objects and try to change the texture of the objects. But if we want to do translation between image and state, this is just no way the CycleGAN can find any clue that which pixel means what XYZ. So if you only do image-based CycleGAN, it will not work here. So what we do here is a very simple thing. We just add a little bit thing, one more step into the CycleGAN model. What we do here, we just adding the time and dynamics into the cycle. What we try to do here is we try to learn the correspondence between these two domains. Not only use the not only saying that the state and image should match between these two domains, but the changes between the two time steps should also match. So we are modeling the changes between the two time steps, and then we say the changes between them also should follow some translation, and then and we use this restriction to learn the correspondence between these two domains of data. So I will introduce this approach in detail. So basically, given the domain AX, which is the real robot like videos, XT and XT plus 1 is basically the image in 2 times depth, and AT is basically the actions taken between these two images. And we also train a forward dynamics model in domain Y, because domain Y is actually essentially some simulation data. We can obtain infinity number of examples in domain Y. So in here, we can train a forward dynamics model, which takes the state and action as input and predict the future state. And so given the inputted data, XT, AT, XT plus 1 in the real world, we first have a model G, which is the state estimator, or the observation translation model that can translate the XT image into Y tilde, and then translate the XT plus 1 image into the YT plus 1 T plus 1 tilde. And then given these two translated states, because in the two different environments, not only the observation, but also the physics, they are different in 2 different environments. So we also need to have a translation model in the action space as well. So we have an HMP, which is translating the AT into UT in domain Y. And then the key part happening here is that we want to use the translated YT tilde and going through this forward dynamics model, which takes in the YT tilde and the UT tilde as input. And we predicted YT plus 1 prime state, which is the state in the next time step. It should be basically consistent with the translated states in T plus 1. So we can see that we are trying to find a consistency between the directly translation in T plus 1 and also the translation results from T and going through a forward dynamics model, which gives you YT plus 1 prime. So there are 2 paths of going from X and to Y in here. One is going through time T and then use a forward model. Another one is going through using time T plus 1 translation model. And then these 2 results should match together in this Y domain. And this is this consistency loss is basically, we can use it to train not only the action translator, but also the observation translator together. So the key here is basically we are relying on the forward model T, and in this kind of cycle, we call it a dynamic cycle consistency. We consider the dynamic changes between YT and YT plus 1 as we are building this cycle. So we not only have translation between the states, we also have translation between the actions, and we use this combination of the state and action to predict the next state. And then this is used to compare to to train both the action translation and the state translation model. So of course, there is also some discriminators happening in both domains. Like we want to restrict the Y domain to be some state space, the X domain to be some images, and this kind of restriction in here. So there are a few variants of our model. So basically, so in some cases, if the physics are the same, so we do not need to have an action translator between the 2 domains. So you can see AT and A is happening in both X and Y domain. We can just train the cycle, which has only the G parameters, the G legwork. So you can see that we can translate X using G to YT tilde, and then YT tilde and AT is forward to the forward dynamics model, which gives you the YT plus 1 prime in the future, which is used to compare the YT plus 1 tilde in the future. And then in the cases where the action is like the dynamics is different in 2 domains, but the observation is the same, we can again train a different model, which is the HMP, to just do the action translation in here. So in here, we basically still have the same domain in state space, but because the physics is different, so we have the different dynamics in two domain. So in here, we can train an action translation model. So we directly just forward the same. So in here, the XT and YT tutor is basically the same. And we can only just train the H and P to complete the cycle. And then of course, we have cases where the actions and the state domain, they're both different. So you have different joint numbers, and because the joint number is different, the action applied on the joint is also different. We can do translation between these two domains as well. So in our experiments, we basically first show some results on just this cross-domain alignment. Essentially, we try to do state estimation in simulation. So given the image on the left as input, we estimate the state using our cycle without action translation. And then we just render this red image in here to show that how the state is actually changing over time as we are training. And after we train this cycle model, we can basically see that given any input image on the left, we can directly estimate the joint state of the half cheetah and then render back in another simulator to get this image. And we can have a very well-aligned actions in here. So why do we want to do this? By doing this, we can actually transfer the policy that is trained on the simulation to directly apply it on this image input. So we can actually train a policy on the state, and then we can apply it on image inputs. So what we do here is basically it's given a policy in domain Y, which is in the state space. We can give the image in domain X as the input. We're going through the translator. We can estimate the state in Y, and then we give this state as the input for the policy. And the policy will output actions. And this is essentially the action we need to take in this domain X. And then we basically evaluate these kinds of policy in different transfer tasks. So basically we have 3 different tasks, and then we show that if you train an oracle policy in Y domain, basically will give you 6,000 reward. And if you directly just transfer this policy to a different domain, basically that you will get a very low reward. But if you use our method to do the transfer, you can basically still get a reasonable reward in the new domain. And here is some more examples. We try to do this translation between these 2 domains under some distortion, and we can see that even we have a monitor behind playing this Gangnam style video, we can still do a reasonable job on moving the robot up and down when the CycleGAN is actually still is completely failing. So another application of our method is basically we can actually train a policy that is in Y domain, which is with 2-leg cheetah, and then we can transfer it to the domain which has a 3-leg cheetah. So we can do this, find this correspondence and transfer the policy directly from Y domain to X domain. So what we do is very simple. So once we find the correspondence in here, so what we do is first we given the image or the state in domain X, we use this G translator to translate the state X into Y domain, which become YT. And then YT, because we already have the policy here, so we can execute the policy in YT to obtain the action UT. And then the UT action is basically use this translation level P. You can transfer back to the action domain in domain X and then become this AT. And then we actually use this AT to do the execution in domain X. So you can see that in this procedure, we are using both the state estimation legwork and the action translation legwork at the same time. So the result is basically we can translate the actions that happens in Y domain to X domain. So here is one more examples that we can do this translation, that once we train the policy in Y domain, which has 3 limbs swimmer, we can translate to this 4-limb swimmer in X domain directly without retraining the RL policy. So are there any questions for this one? There's a question how to describe the action A and U so that you can apply. So the action A and U is basically some velocity control, the positional control. It's like probably for half cheetah, it's like 14 or 17 kind of dimension action. So the HMP is just some MLP that takes probably 14 dimension input and output a larger 14 or 17 dimension output. Okay, seems like what if the friction changes? Yeah, so the point is that if you have friction changes, what it means that is that you did by taking actions in X domain, the same action taken in Y domain will lead to different results. So that's why we actually need to change the action. So changing the actions, finding the correspondence between the action is essentially handling the physical gap. So you can think of like, if in domain X, we have the 2 times friction as domain Y. So by using the actions like moving 1 meter ahead, probably means that it will move the objects 2 meters ahead. So then in this case, we need to have a translator to scale the action half. So we can apply the half action to the Y domain, which leads to similar results. Yeah, it's in the HMP function. Do we have to repeat whole procedure again if we want to translate to a third domain? Yes. The one of the limitation in here is that we need to collect data from both domains, or it can be collected randomly unpaired data. But we do only train this translator between 2 domains. It's not extendable directly to the third domain. Okay, I think I can go very fast in the last part. So finally, I want to talk a little bit about some multitask learning that we did that we can train a policy that is generalizable across different manipulation tasks. So the manipulation task we do here is using this MetaWorld environment that you can see. You have a Sawyer arm. You try to do a lot of different tasks: opening window, closing windows, open drawers, closing drawers. And then the problem of this multitask reinforcement learning is that if we like when it is doing 10 task multitask learning, it is still fine. But when we try to extend to 50 tasks of multitask reinforcement learning, we can see that training a single policy for each individual task is much better than just train a single policy for all the tasks. So the reason here is that, so there are basically 2 reasons. So you can see if you want to train a policy that have multiple heads and try to solve multiple different tasks, there can be a lot interference between different two tasks that is not relevant. For example, like opening a door and insert the pad might not share a lot of elements. Besides, you need to reach to the same, reach to the target location. So there can be a lot of interference when you train multitask together for multiple tasks. And then if you only train a very plain multi-layer perceptron, it's not very smartly trying to reuse the components across similar tasks. So we do hope that for unsimilar tasks, there should be less interference. But for similar tasks, we hope there should be more sharing across different tasks. Like closing window and opening a window should probably share a lot of skills in these 2 tasks. So what we try to do here is just try to propose a new modular architecture, which is composing by the base policy legwork and the routing legwork on the right. So on the left, base policy legwork will have a lot of different small modules, and then you can think of each module is representing some skills that the robots need to learn. On the right is the routing network, which is trying to output the probability to how to compose these modules to finish different tasks. And with different routing, we can have different policies by composing different modules on the left. So we kind of make it soft, which makes it differentiable. So what we do here is essentially on the right, on the left, there's a lot of different module. This module is just some multi-layer perceptron. On the right, given the task embedding as input, we can basically output the probability to basically representing how to combine these modules together. So for example, here we can output a probability to 0.4, 0.6, which means that to get the input for the module on the top right, we use 0.4 multiply the output of the module on the top bottom left, and 0.6 multiply the output of the module on the bottom right. And then we sum them together, we get output for the input for the module on the top right. And then here is another examples. We can just basically have mixtures of different soft mixtures of outputs from the input to the next layer. So given different tasks and different state inputs, we can input different routings and have different ways to combine this module together to solve different manipulation tasks. So here is an example. So we just use 4 modules in each layer, and we have a 4-layer modular network. And we can show that in each time step and for different tasks, the routing strategy is changing across time. So the red and so the dark red means there's a high connection, and then the lighter color means there's a low connection between the 2 modules. We do see that across different tasks, there are similar connections. For example, in this push and close door, in this particular time step, we can see that the upper part of this module network is actually sharing the routing strategy. So there's actually some sharing across different manipulation tasks. And then similarly, here is another examples. And then we can see that even these 2 tasks, they're not completely the same, but they're opening something. So at a particular time step, they actually share the module connections across these 2 tasks. So we basically show some examples that we are actually getting much better results than baselines. There are also some TSNE plots, basically showing that the routing, we kind of plot the routing in 2-dimensional space and showing that for similar tasks, the routing is close together in TSNE space. For not similar tasks, the routing strategy is far away in the TSNE space. So that's basically all of my my topics today. So I've talked about some adaptation using self-supervised learning. So we try to transfer across different visual background, different physical and dynamics environments. And we also talk a little bit about how to do this multitask reinforcement learning, do sharing and transfer across different tasks. And I'm welcoming any more questions. Okay.
So, hi, Dr. Wang. Thanks so much for the talk. So this is more of an open-ended question. So I was wondering what your thoughts on test time learning are. So recently there has also been a paper on test time training in classification, where they use auxiliary tasks just like you did. So do you think that's a way forward when it comes to generalization or robustness?
Yeah, so I do think so, because so I guess there's you can, it's not just for self-supervised learning, you can generalize it for probably a test time adaptation. You can I do think test time adaptation is necessary. So there are also other strategy to do that. For example, the routing network I just introduced is sort of an adaptation. And then people also do this conditional convolution, dynamic convolution. It's basically it's like input different environments. You need to adapt the legwork using different ways to handle different environments. So you have a very dynamic structure of the legwork flexibly updated to the new environment. So I would see test time training is a way to use self-supervised learning to do this kind of adaptation. And then there's also many other ways to use dynamic convolution or use this routing strategy to dynamically adapt the legwork to the new environment. But I do think that in general, the adaptation during test times, you condition on the input testing image to change the legwork. The, the, the thoughts here is very important. So instead of training invariant representation, you can have different ways to adapt to the current image.
Okay. And on a related note, so do you have any insights on how to choose the self-supervision task? So for
Yeah.
example, in your case, like you've used inverse dynamics, and in classification, people use the rotation prediction task. So is there any connection between the main task and the auxiliary task?
Yeah. Um, so I think in our case, we do find that there's a strong connection because the inverse dynamics model, we are doing some control task and manipulation task. So the inverse dynamics model here is actually very relevant to the RL task because they all both input some state and output some action. In our paper, we also actually show that we use the rotation task. So in this case, it does not help much on controlling tasks, but the rotation task actually helps in the navigation task where you give a scene and then you need to navigate inside the room. So rotation task actually kind of how you capture the structure of the scene. So in that case, so we find that rotation task is better than these control tasks for navigation. So it does seem like that there are different self-supervised that is good for different mainstream tasks. We also have tried to actually study this problem. Can you automatically do some selection to give a higher weight to some self-supervised tasks and lower weight to other self-supervised tasks during and then try to learn this adaptive way for multi-task learning, but it doesn't go so well, and I don't think there are actually many successful cases on learning how to select self-supervised tasks to help the mainstream task. A lot of what I have seen is all improve like 0.1% in CFA dataset. Is not very generalizable right now, so it's still a very hard problem.
Okay, thanks a lot.
So there is a question on by Shin. Is there any formal definition of the generalization in RL, such as like MDP distribution of the training and testing environments? What are the differences between generalization and transfer learning in RL?
Yeah, I mean, in here it's essentially the same. Is transfer learning generalizing to new environment. At least I'm referring to the same thing. And then so specifically I talk about actually the transfer part, especially in the second word. It's mostly about transferring policy that is in different physical environment, different morphology, and different visual input. So I think generalization is really a very broad term. Essentially, anything machine learning that is involving training and testing, you can do. You can call it generalization. Um, but specifically in here, I'm trying to basically tackling the task that is visually different. Physical is also different. Morphology can be different. How do you do this? Transfer learning between these different domains flexibly.
So there's another question. This is about the last topic. So does the model decide which tasks are similar and thus decide those should share the same parameters or something?
Yeah. So does the model decide which tasks are similar? So I think it does during learning. I think it just gradually emerged um, to the model just gradually emerged to know which tasks to sharing the skills that is beneficial for better reward. So we do not have any prior knowledge saying that this opening and closing window should share more. It's just after learning these two tasks by using their own rewards, and then we find that their routing is very similar in here, so they share the tasks.
Just a
So,
follow up to that, is there a like a predefined list of modules that you think of, like there are 10 tasks, that's why you need 10 modules, or like
No,
it's
there's
discovered?
no, yeah, yeah, it's not, nothing is predefined here. So it's more like a implicit. So there's actually not explicit meaning for each module. It's just some MLP. We didn't give a definition on each module. You can think it as just a small network. And how to combine this small network together to learn this task is all automatically happening here.
And like, but is there a like definition of how many such small networks do you need, or it's that also
Yeah, so we
hyperparameter?
did pretty that. So we tried different combinations. Like we have four modules in 4 layers, and we also tried 2 modules in 2 layers. It's just generally seeing for more tasks, it's better to have more modules, but it does not have a specific um, like a number that we need to use for a specific number of tasks.
so I had a follow up based on this. So, did you discover that maybe two unrelated or unintuitive tasks were helping each other? Um,
Um, So I think not so much. So I do find a lot of times it's the opposite. That the two tasks that is intuitively should help each other, but it's not. For example, like there's a pick and place, and then there's a reaching. So you will see think that to the pick and place, you first need to do reaching to the object, and then you can pick up the object and then you can place. Um, so we even initially try to do some kinds of incremental learning. So you first train the reaching, and then you train the pick and place using this kind of module. But somehow we didn't find it this first train the reaching and then train this pick and place is very helpful in here. So it's actually it's not very intuitive why um, pre-training a subset of the task is actually not helping to solve a more complex task. Um, so I guess it's some optimization in reinforcement learning here. It's not, although they are very similar tasks, but they are still not very aligned. Yeah. And I think as I know that this phenomenon actually happens a lot. Like for example, in the OpenAI hide and seek environment, that the two agents play with around the two agents. So they told me that they also have tried to pre-train all the physical skill, how to climb the ladder, how to move the wall or something, and then try a general policy on top. And then also find that training from scratch is doing as well as and as fast as using these pre-trained primitive skills. Um, so it's an interesting problem that to solve. How can we actually use pre-training better in reinforcement learning? So I think it's still some people are still I think people are starting looking into it, how to use offline RL or pre-trained data set to do that, but it's still an open question.
Folks, if you have any more questions, feel free to ask.
Okay.
Okay, looks like okay. So just like one more thought over the test time learning. Do you
Mm-hmm.
think like analysis of work, like what kind of weights the self-supervised network is trying to activate compared to the weights the actual target task is activating, we can identify better, say, self-supervised methods which are more useful during the test time.
Yeah. So that's one approach which I have actually tried. So basically, it's basically the gradients. So we do try to like for example, if you fine tune a self-supervised task, you get the gradient. You fine tune another self-supervised task, you get a gradient, and then you see which gradient is more aligned with the reinforcement learning gradient. If
Yeah.
these two gradients more aligned, then probably the more aligned self-supervised task is better for the reinforcement learning task. So we should make that um, higher weight.
Yeah.
We actually tried that, but it still turns out like um, I think a lot of approach is already using this kind of gradient alignment to try to weight the multitask learning. But so as we try so many experiments, I find gradient alignment is really unstable because the gradient is also changing a lot. Depends on the input, depends on the training stage of the legwork. So empirically, I find I'm not very convinced that it can actually help. Although there are tons of papers published in this area, but at least I could not find very um, convincing and reliable open source code to make it actually good. We actually also try for a few months in this direction, but it's not finding. Yeah.
Okay, as I think we are running out of time, so we will like to thank you, Professor Wang, for this delightful talk. We learned a lot, and
Thank you.
hope see you soon in
Yeah.
ICLR.
Yeah. See you.
Thank you so long.
Thank you.
Thank you. Bye.